We're going to have you do some reading for Monday for section, basically looking at a simulation study. So just to give you a heads up about that, we'll give you the information probably this morning. And I should also be getting out information on the final projects within the next few days, so I'll give you some information about that as well. Let's see. Okay, so picking up from last time, I just wanted to say a couple words just to close out this example of the precision matrix that had a zero eigenvalue, and then using the pseudo inverse. So just, I think I may have, as I was presenting this, I may not have been as clear as I could have been. So let me just say a couple more words about this, which is basically if you have this model, this is this first order smoothing model that says the expected value of any y, think of this as a time series, is just the mean of the surrounding y's. That then tells us, if you work through the underlying details, what you would see is that the precision matrix, the inverse of the covariance matrix, is a matrix A that has a form like this, where the fact that I've got these dashes in here just indicates I'm not specifying exactly how many time points I have, but this is the general form of the matrix. It's banded like this. And so if we now want to think about what's the covariance, well, as we saw last time, this has a zero eigenvalue. We can't just invert this matrix because we would end up with an infinity as one of the eigenvalues of the covariance. So we can't get A inverse, which would be the covariance of the y's. So instead we do A plus, and that's where we take what we had from here we had a lambda I that was equal to 0, so 1 over lambda I, which is now going to be the eigenvalues of the inverse matrix, would be infinity, and instead we're going to set that to 0, and that's going to be the A plus that we get. So basically what we're doing is instead of using A inverse, by using A plus, we're inducing this constraint that allows us to then work with the problem. Okay, so questions about that? Okay, so then I also asked you for today just to think about a few of these linear algebra problems just to sort of warm up and practice for what we're going to be talking about over the next few days. So I just threw those up here. I mean, I don't want to necessarily go through these in terms of every line showing this, but just to get a feel for what's going on here. So if we look at this matrix and x is n by p, that means this guy is going to be p by p, and this guy is going to be p by n. So this thing is singular. So I can think about that in terms of thinking about what the rank of this is. So what's the rank of this guy? Okay, why is it P? Okay, so it's invertible, so it's not going to be less than P. Why can't it be more than P? Because there are only P rows and only P columns, so it can't be any more than that. Okay. So this guy has rank P. If we do the inverse, we're still going to have rank P. We're just going to be taking the inverse of the eigenvalues. We're still going to have as many inverse eigenvalues that are non-zero as there were to start with. We're going to have P eigenvalues that are non-zero. So now what we should see is that the rank of H is still going to be P, but the dimension of H is going to be n by n. So why is the rank of H going to be P rather than anything larger than P? So what am I, let's sort of ignore this x for the moment. What am I doing when I take this matrix and multiply it by another matrix? I'm getting linear combinations of the rows or columns of the x transpose x matrix. So I can't increase the rank any, because all I'm doing is linear combinations of the original, say, of the original columns. So that's going to, so the rank of this is going to stay at P even after I multiply them by this, and by the same token, when I'm pre-multiplying by x, the same thing is going to happen. So I'm not going to increase the rank relative to the rank of this inner matrix here. Okay, so any questions about that? Okay, so the second question was relating actually back to that example, that case study that we're looking at on Monday. So we've got some covariance of y that's equal to some eigendecomposition. And if we have an eigenvalue that's 0, for example, when we zeroed out the eigenvalue to get the pseudo-inverse over there, well, that eigenvalue that we zeroed out corresponded to an eigenvector. We saw this in the example last time. That was just a constant. I think it was like 0.44 when we looked at it on the computer, times a vector of 1. So we've got an eigenvalue of 0 that corresponds to the constant vector. And then the question is, why is the sum of what we saw when we summed up, we took one realization, a vector y, that was a single realization. And when we looked at the sum of that, we saw it was 0 up to numerical precision. It was 1 times 10 to the minus 15 or something like that. So we can ask, why was that sum equal to 0? And in fact, what we would see is that any time that we sampled a random vector y according to that recipe, we would get that the sum was 0. Well, that says, okay, the variance of this is this sum is 0. What is this? This is just the variance of a vector of 1 is transpose times y. And now we can think about why that's the case and relate it back to the eigendecomposition. So we've got this is equal to 1 transpose times the covariance of y, which is gamma, and that gamma transpose 1. What do we know about gamma? What are the properties of the columns of gamma relative to each other? So it's an orthogonal matrix. So if we take the inner product of any of the columns, they're going to be 0 unless we're inner producting them unless we're doing the inner product of a column with itself, in which case we would get 1 because it's orthonormal. So each of the vectors is normalized. So what's going to happen when I do this? I'm taking the inner product of a vector of 1s times each of the columns of gamma. So think about one of these is c times 1. So right there. Just going to get c times n, I guess, right? So so this is going to give me n different numbers. Right? In the ith position, I'm going to have some constant. Times n in this case. What am I going to get in the other positions? I'm going to get a 0 because this column and 1, these are basically the same vector, just this is scale, right? And I know that all of the columns of gamma are orthogonal to each other. So if I multiply one column times another in a product, I'm going to get a 0. So this times any column this times any column of these guys except for this one is just going to give me a 0 by the orthogonality. So this is going to be a whole bunch of zeros. Similarly over here, I'm going to get the same thing. And now I can think about what does my eigenvalue matrix look like. This is a diagonal matrix. Lambda 1. Except I know that lambda I is 0. Right? That's the one. That's the direction variation of basically 0 now. So this guy is actually a 0. And now if I do this multiplication, I'll see that I just get 0 out of this calculation. Okay, so that says that by doing this, I am indeed inducing a constraint, and if I look at that constraint in a different way in terms of covariance, I see that it does indeed satisfy the sum of the y's. Okay, questions about that?
So the sigma yi necessarily be 0. I mean, the variance is 0. So what about its value?
Right. So when I was looking at this and generating, right, if I add on a mean, then actually that sort of ties in nicely with the point that I made right at the end of classes. We were sort of wrestling around and cleaning up, which was that I can parameterize a statistical model that would be some mean plus y, and I could have y be normal 0, mean 0, and then this covariance. So the idea is you could still introduce a mean if you wanted to, but the way that you would think about this model is that you would you'd be generating y normal 0 with this covariance, and then you could add in the mean if you wanted to. Other questions? Okay, what about the determinant is the product of the eigenvalues? So I have some matrix, A. So I can write this as the determinant of the eigendecomposition. Right. So now what can I do? I can look at the product of the determinants instead of the determinant of the product. So I've got lambda. I'm going to move this one over here because now I'm just multiplying numbers together. Okay, and then by a variety of ways, you can see that this is just going to give us a 1. In fact, one way to do it is just say, well, this is just gamma, gamma transpose. This is just, these guys are orthogonal, so same ideas over here. I'm going to get the identity matrix here. That's equal to 1. And now I've just got this, but this is just a diagonal matrix, and on the diagonal are the eigenvalues. So I'm just going to multiply the eigenvalues to get the determinants. Okay, so this is not a linear algebra course, but it is useful to remember and be able to do sort of these basic kinds of calculations and reasoning. All right, any questions? Okay, so let's now turn and talk a little bit about some principles related to computation when we're working with matrices and doing linear algebra calculations. So the first thing I wanted to mention is there are a few ways to get good speed if we're doing linear algebra calculations. So one of them, but in many cases the least important factor, is to have a fast computer. Okay, so if we increase the speed of the hardware, we're usually going to get a faster calculation. Oftentimes what's much more important, and where over the past few decades we've gotten orders of magnitude improvement in calculation speed, is to come up with a really good algorithm to do the calculation. Okay? And then the third piece of it is you could have a good algorithm, but if you don't implement it in an efficient way that takes account of what are the properties of your hardware, then you may not get all of the benefit from the good algorithm that you could get if you implemented it appropriately. So fast computer, good algorithm, efficient implementation. And then the other thing that we're generally going to be talking a lot about is that we want the algorithm to be numerically stable. So we want the algorithm to do the best job it can of giving us as much precision in our answer in light of the fact that we can't store numbers infinitely precisely on a computer. So we want to take account of the issues that came up that we discussed in the last unit. Okay, so this is, I'll give a quick example. This is, I guess you could either think of this as an algorithm or just as an efficient way to implement an algorithm. But if we just think about the simple case of multiplying a matrix times a vector, and this also illustrates how we can also think about these kind of calculations in the context of hardware. So I have some matrix and I want to multiply it by a vector. So this is basically going to involve two for loops in one way or another. Okay? But I could think about it in two, and maybe there are other ways to think about it. I could think about this as taking this vector and doing it as an inner product, a dot product against each of the rows of this matrix. Okay? So that would be one set of for loops, right? I would do the for loop. I would do an outer for loop that is basically looping over rows, and then I do an inner for loop where I'm looping over the multiplications of the column by the appropriate row. So we can think of that as basically, okay, so I sort of like to write these things out like this. I like to sort of write these things out in a sort of graphical way that sort of lets my brain think about what the calculation is. Well, okay, it's just this times this times this, etc. But we could also think about it in another way, which is I could think about this vector, let's say that's x1 up through xn. I could think about this column times x1 plus the second column times x2, and so on and so forth. So that could be this times x1 plus this times x2 up through this times xn. Okay, so that's also two for loops, but it's writing the code in a slightly different way to do in terms of what calculations I'm doing. Well, now we can say, okay, well, which of these is going to be better? Well, it's exactly the same number of calculations, so in some sense we should think of these as being equivalent. There's no magic here, right? I'm doing the same number of multiplications and sums overall. But if I think about the fact that in R or in Fortran that numbers are stored column major, this one's going to be likely a rather more efficient implementation if I think about the computational setup under which I'm working. Because with this one, I can just loop through these guys, and then whenever I'm going and fetching values here, I'm fetching them in order from computer memory. Okay? Whereas this one, you know, I've got this, if I think about, you know, the computer memory, it's all strung out here. If I need to fetch this guy and then this guy, well, that's fetching this guy, and then I have to go over here to fetch this guy, and then I have to go over here to fetch this guy, and so on and so forth. So you should actually be able to do a little demonstration of this in R. If you coded this up in R and did these calculations, you should see that this way of doing it is somewhat faster than doing it that way. Okay, so questions about that? Okay, so the next thing I want to do is highlight this question of relating what we talked about in the last unit in terms of numerical accuracy to thinking about numerical accuracy in the context of linear algebra. So we're going to start with a problem that's not directly related to the accuracy with which you can represent a number, but will lead nicely into that. So in general, the idea is that a calculation is ill-conditioned if we make small changes to the values that are being used in the computation, and the result is that we get very large relative changes. We get much larger changes in the resulting answer. So one way that numerical analysts quantify this is they quantify the condition number of particular calculations. So oftentimes we're going to be doing calculations that are basically matrix inverses and solving systems of equations. So in the main condition number that we're going to be thinking about is the condition number of calculations that look like that. Okay, so it turns out the condition number, as we're going to see, is the L2 norm. So the condition number in terms of the L2 norm is the ratio of the absolute values of the largest to smallest eigenvalues of this matrix A. And as that ratio gets larger, the accuracy with which we can do the calculation degrades drastically. So we're going to see that here in this context. So suppose I'm trying to solve this set of equations, this system of equations. So I've got so each row of A represents coefficients that I'm multiplying by x, and then I'm getting my answer in the appropriate element of B. Okay, suppose that B is this vector and A is that vector, and I solve this system of equations to try and find x. Okay. So if I do that, what I'll see is that, okay, if I do that mathematically, the answer is just x is 4 ones. So that matrix A times this gives me that answer. But if I change B by just a little bit, I basically add or subtract 0.1 to each of the elements of B, I'm going to say that's B plus some little perturbation to B, and I'm going to call that delta B, the perturbation. Well, the answer then is going to be x plus some perturbation. Okay, that's my new answer if I use B plus delta B instead of B. And the answer I get is this. Okay? So delta B is really, really large because the difference between x and x plus delta x is really quite large. Okay? So this sort of violates a bit of our intuition. Like if we look at this and you know, if I asked you, maybe I should have done this exercise, I say, okay, if I change from B 32, 23, 33, 31 to that new B, do you think the answer is going to change very much? We might have said, you know, it'll probably shift things around a little bit, but maybe x would be, you know, 1.3, 0.8, 1.05, something like that. But we've gotten a very drastically different answer. Okay, so the question is what's going on? And the way that we can think about this is using this idea of a condition number. So I won't go through the derivation of this. It's in one of the books that's referenced in the syllabus, and I think at the beginning of the unit. But if you do some manipulations with inequalities and norms, and we're going to see a variation on this calculation where we actually work through the details in a minute, what you'll see is that for this problem of ax equals b, that I can write that the relative change in x, so the perturbation in x relative to the magnitude of x, or the magnitude of the perturbation in x relative to the magnitude of x, is less than or equal to the norm of A times the norm of A inverse times the relative change in B. And this is the condition number of, this is that product of those two norms is the condition number for A with respect to inversion. So you can work out, and we're going to see this in a second, that this is just the ratio of the largest magnitude to the smallest magnitude eigenvalues. And so if we actually see this in action, okay, so I have a little function norm 2 that calculates the length of vectors. And I've got my matrix A, my matrix B, my perturbed matrix B, and I'm going to find x by solving this system of equations, and I see that the answer up to numerical precision is indeed 1, 1, 1, 1. Okay. But now if I change B and solve the new problem and look at x perturb, I see, okay, that's the 9.2 minus 12.6, 4.5 that I showed you on the previous, on the actual slide. Okay. And I can calculate these various norms. And so what this is right here, this is the length of delta x divided by the length of x. And in our little rule of thumb here, we said that was less than or equal to this condition number times that ratio of norms of lengths of the B pieces related to B. So that's what I'm doing here. Here's the ratio of the largest and smallest eigenvalues. And here's that relative size of the perturbation in B and the size of B itself. So the length of the perturbation in x relative to the length of x was 8.19, and now if I do this, I get 9.94. So my inequality that I gave you on the slide holds. I've got, this is an upper bound, and this is a bit lower than that upper bound, but it's reasonably close. So it gives us a sort of ballpark figure of what we could expect. So what we see is that when we get a disparity, a relatively large, well, I guess we should go look at it. What are the eigenvalues of E? They're relatively different, right? So one of them is 30. The largest one is 30, and the smallest one is 0.01. So this is like 4 orders of magnitude difference in the eigenvalues. And that difference in magnitude is what drives the fact that when we solve these two different problems that look like they should be very similar problems, we get rather different answers. Okay, so first off, let's see this idea that we can do that the L2 norm of these matrices is the maximum eigenvalue. So if I want to think about the L2 norm of A, then that, by what you would have seen in the earlier, just what I wrote up earlier on in the unit, I can write this as the usual L2 norm, the length of a vector, of this vector for Z, such that so I'm going to do this. So this is the supremum of Z, such that over Z, such that the length of Z is equal to 1. So I'm trying to do that calculation. Okay, so this here is equal to, it's equal to the square root of A Z transpose Z, which is equal to Z transpose A transpose A Z. And now I can play around with the eigendecomposition of A and insert that here. So I'm going to get Z transpose gamma transpose lambda gamma transpose. So if I transpose that, that's just going to give me the same thing. Gamma transpose lambda gamma Z. And this is just an orthogonal matrix times itself. That's just going to, so the gamma transpose is the inverse of gamma, so it's just going to give me a 1, and the identity matrix back. So now I've got square root of z transpose gamma transpose lambda squared gamma z. But multiplying by this orthogonal matrix is not going to change the length of z. So I'm just going to replace this. I'm just going to call this y. Call it z star, I guess. So now I've got some y lambda squared y. And again, I haven't carried along the soup here, but so now this is equal to the supremum over y such that the length of y is equal to 1. Okay, and now I have an easier problem to solve because this is just a diagonal matrix. So what is this? Well, this is just the sum of lambda squared, the sum of yi squared times lambda I squared. But I have this constraint that the length of y has to be 1. And so if I think about sort of pairing up yi's with lambda i's, what I want to do to maximize this is I want to pair up the largest possible yi that I can get with the largest magnitude value of lambda I. And that's going to happen if I choose yi to be, if I choose to have yi be yi equals 1 for the maximum absolute value of lambda I, because that's basically going to sort of line up the biggest possible element of y with the biggest possible element of lambda, and that's going to do the maximization. So that's when I get the maximum. That's what I need to do to get the maximum, and the maximum actually is, just 1 times lambda I squared. So the maximum, so this supremum is indeed, and then I have to take the square root of it, so this supremum is going to indeed be the maximum of lambda I. So that's the maximum magnitude eigenvalue. I can play basically the same game with the inverse, and so the result is going to be that the result of this is going to be, I'm going to get the largest magnitude eigenvalue divided by the smallest magnitude eigenvalue here as the condition number. Okay, so questions about that? Okay, so the whole reason for doing that was to then try and think about what happens if we are trying to solve a set of linear equations, system of linear equations on a computer. So I have ax equals b. If I'm a mathematician, I look at this and say, okay, assuming that this matrix A is invertible, I can do this, I don't have a problem. But if I look at this from the perspective of a numerical analyst, I say, well, you know what? I can't actually write down what b is. I can't actually on a computer represent what b is precisely. Nor can I write down what x is precisely. Nor can I write down what a is precisely. So if I start with a and b and I'm trying to find x, I can't pin these down precisely, and so I'm going to end up with error in this, and I want to try and get some quantification of how much error I'm going to have in that. And the issue is not going to be, I know that if I could just do this calculation exactly and then put x into the computer, I know that I'm only going to be able to represent x to a certain amount of precision, 16 digits of precision like we've seen. What I'm going to see is actually even worse than that in actually coming up with and computing x on a computer, I'm going to lose digits of precision, so I'm going to end up with fewer than 16 digits of precision. And the question is, how many digits of precision do I lose when I'm doing this sort of calculation? Okay, so one way to write this in terms of the problem that I'm actually solving on a computer is I'm basically solving this problem, where this again stands for perturbations in each of these quantities. And the idea is I want to get some idea of how big this is, given that these guys are the elements of the perturbation in elements of B and the elements of A. The perturbation there is on the order of 10 times 10 of 10 to the minus 16. But that's the relative error that I'm working with. Okay, so where am I here? Okay, so the idea is let's work through this in some detail to see what we get for this loss of precision that I've been mentioning. Okay, so the idea is I have A plus delta A times X plus delta X equals B plus delta B. And I want to manipulate this to get something that looks like an equation like this, where I say, what's the relative error in my answer for X? Okay. So that's where we're trying to get to. Okay, so if I just multiply this out, I'm going to get AX plus A delta X plus delta A X plus delta A delta X plus B plus delta B. And now I'm going to get A delta X. I'm just going to move everything to the other side. I'm going to minus AX plus B. I'm going to group that together. Minus delta A X minus delta A delta X plus delta B. Well, what do we know about this? Well, I'm trying to solve this system of equations, so I know that's equal to 0. So that's going to disappear. And then the other thing to notice here is that when I'm thinking about this, as long as things are not too ill-conditioned, that this is a term that only has the perturbation. Let's see, how am I motivating this? Well, I was going to say this. So this has the actual X in it, and this has the actual A in it. So we know this is going to be rather smaller than these other terms. So we're going to leave that out as being approximately equal to 0. Although as I'm now staring at this, I'm not sort of seeing why I wouldn't use that same logic on this term here. All right, I think I'm going to leave this in here because that's part of the derivation, but I'll try and figure out what the motivation is for leaving that and taking this one out and let you guys know about that. Okay, so we've got these three terms left here. And now I can do A inverse times each of the sides. So I'm going to get it delta X equals A inverse. So I've got minus A inverse times delta A times X plus delta X. Oh, okay. I guess if I took this out, then I wouldn't have delta A in my resulting expression, which is going to be an important part of the expression. So I think that might be the reason for that. Okay, so now I can use. Now what I'm going to do is I'm going to take the norm of each side of this, and I'm going to use the triangle inequality and say, okay, delta X is less than or equal to, let's see, A inverse delta A X plus delta X. But then I can use the triangle inequality with respect to this and say this is X delta X. Okay, so I've got a whole bunch of these norms in here. And if we sort of use this as where we're something like what we're trying to get to, let me put in an A, the norm of A in here. Okay, so I'm going to multiply and divide by that. So I'm going to have, so I've got this, so I've got, let's do A, then we've got A inverse, and now we've got delta A over A, and I'm going to do this as delta X over X. So I'm going to move the X to the other side, and now I've got, what am I doing here? I've still got X, I'm losing a term here. so I've got, actually, I think I want to leave that there for now. It looks like. So what do I have here?
It's like multiply and divide by the same term.
Yeah, I did that here.
Then you want to divide by norm of x. That way it cancels out the equality. So you have delta x over x is less than or equal to a times
Yeah, that's where I want to get to. I think the steps that I have here are slightly different than that, so let me stick with this. Okay, so I've got x plus delta x. So wait, sorry, what did I do here? Okay, so I want this to be, this here, x plus delta x. Okay. Okay, so now I've got, I'm now going to do this as delta x, and I'm going to call this kappa of A, so that's going to be my condition number. And I had x plus delta x here. So I'm going to rearrange terms, and I'm going to get 1 minus kappa of A times delta A over A. And that's less than or equal to kappa of A times delta A over A times x. Okay, so I've just basically multiplied things out, moved a term onto the other side, rearranged things so that I can express it like this. Okay, so what do I see here? Well, the thing that this helps me to do is if I look at this, as long as the perturbation in A is small relative to A, and this is basically going to be a function of the precision with which we're representing numbers. So this is going to be something like 10 to the minus p. So that comes from the previous unit when we talked about having 16 digits of precision. So in the usual case of how we represent floating points in double precision, this would generally be about 10 to the minus 16. And for the moment, let's assume, so let's say that this condition number is 10 raised to some power t. And the idea is if the problem is not too ill-conditioned, then this is going to be small relative to this. And so this whole thing is going to be basically about, this is going to be basically about equal to 1. So this term is going to be about equal to 0. If we're not at a point where the ratio of these eigenvalues gets to be something like as big as 10 to the 16. Okay, so this might be, 10 to the 5, 10 to the 12. That divided by 10 to the 16 is going to be quite small relative to 1. So the result is we're going to get delta x over x. I'm now going to move this x to the other side. Is less than or equal to kappa of A times delta A over A. Okay, so what does this tell us after we've worked our way through this? So this says, okay, this is the relative error in our solution x, which is the thing we're trying to find when we're solving this system of equations. And that's less than or equal to the condition number times the relative error in A. And if you sort of play around with the fact that each of the elements of A has a relative precision of 10 to the minus p, or 10 to the minus 16 in double precision, you'll see that this is basically 10 to the minus p, and then in our case usually we have p equals 16. So what this says is, and if this is 10 to the t, what this says is I basically have 10 to the t minus p as the relative precision with which I can represent the answer. So let's suppose, so if p is equal to 16, and let's suppose t is equal to 8. So suppose the condition number, the ratio of the largest magnitude to the smallest magnitude of eigenvalues is something like 10 to the 8th. Then what that says is the relative accuracy with which I can represent the answer x is going to be something like 10 to the minus 8. But remember, I started this whole problem saying I can represent numbers with relative accuracy of 10 to the minus 16. So this basically says I've lost 8 digits of accuracy in the answer relative to what I was hoping that I would achieve. And so basically, we're going to, the name of the game here is going to be find the condition number and see whether t is getting to be up to something like 16, or is it much less than 16. And that will tell us basically the magnitude of the error, relative magnitude of the error in our solution x here. Okay, so questions about that? Comments? Yeah.
So I think the derivation, when you're doing the delta a times delta x, that thing's going to be 0 because it's some higher order terms, like 10 to the minus 32. That way you don't even need to subtract any of the delta x times kappa of a part.
So you think if I left this out,
yeah, if you left that out, then
that I could still work through this. So I guess if I left this out, I'd still have the minus a inverse, and I'd have this here, and I'd multiply and divide by a again here. Right. So I'd still have that. So what would I be leaving out? I would have left out this term, which is this guy here. So I wouldn't have this guy here.
So then the thing would already be 1.
Right, okay, so this guy comes over, right, so I just end up with this x and this guy here. Okay, so that avoids me having to even think about this.
Right.
Okay, thanks, that's a nice catch there.
I think the reason delta b is 0 is because you're perturbing a. That way it's just going to be a perturbation of a and perturbation of x. And so you would be fixing b. You wouldn't actually be perturbing it at all.
Well, it's not that I'm perturbing it, it's that I want to solve a system of equations where I know b, but I can't actually put that into the computer and have it exactly be b. I can only represent b up to an error of 10 to the minus 16. So yeah, you're right. I'm not perturbing it, but as soon as I put it into the computer, it's perturbed.
Yeah, so I don't really understand why it's necessarily 0 then.
Well, it's because the size of this, where did I write this out? Okay. So if I'm thinking about the size of these various terms, this is negligible. Okay, leaving aside this one, which as you hopefully point out, we don't need to think about. The size of this relative to these. Oh wait, I see what you're saying. Well, these guys. Let's see. So this is going to have some magnitude. And then this is going to be something like 10 to the minus 16.
Right.
But that's, okay. But if this were just like a magnitude of 1. Yeah, I don't have a good answer for that off the top of my head. It might be that if we left it in and then sort of worked our way through here, we would be able to sort of see something like this that would suggest that we don't need to pay attention to that term. But let me think about that offline and see if I have a better answer for you.
Okay.
Other questions? Okay, so that's basically what I said here. So let me say a little bit about improving conditioning. So I've already sort of had the theme going that oftentimes we're going to be able to fix numerical problems with a fairly simple solution. So we've already seen that once or twice. So let me show you an example of that here. Okay, so let's suppose that I'm doing a regression problem and I have a column of my regression matrix that is, suppose I'm regressing on time, and this represents years, and I'm including that as one of my covariates in the model. And suppose I'm going to regress on the years 1990 up through 2010, and then I'm going to regress on a quadratic term in those years. So I'm fitting some quadratic term in time as well as a linear term in time. Well, if I now construct my design matrix, my covariate matrix, from x1 and x1 squared, so let's think about different ways of constructing a representation of the linear term. I can just represent the linear term as just directly as time 1998 to 2010. I can think about subtracting off the mean of those values as my linear term, so I can still do an equivalent regression from that. Or I can think of, so that's going to center one of the columns of my X matrix. Or I can think about dividing by both centering and scaling with that column of my X matrix. So those of you who've seen regression, which should be all of you, you've probably seen this idea of manipulating the X matrix to basically center and scale columns of the matrix. And so let's see what effect that has in a numerical context. So I'm going to create 3 possible design matrices. So here's X1. So that's got an intercept column, a linear column, and a quadratic column. And here's X2. That still has an intercept column, it still has a linear column, and it still has a quadratic column, but I've centered the I've basically centered the linear column and then done the quadratic on that. And then X3, same business, but now I've done both centering and scaling in terms of, and we see what the result is in terms of my linear term and my quadratic term, the linear column and the quadratic column. Well, let's look at the condition number of the X transpose X matrix that I create from these 3 different design matrices. So first I'm going to do the eigendecomposition of the cross product X1 transpose X1. And if I look at the values, what do I see about the ratio of the largest magnitude to the smallest magnitude eigenvalues? It's just absolutely horrible, right? I've got 10 to the 14 divided by 10 to the minus 8. So the condition number is 10 to the 22. 22 is much, much bigger than 16. So I basically lost all of my digits of accuracy in doing any computations if I go back to this motivating calculation over there. So just doing the naive regression by throwing in the quadratic of these large numbers in the 1990 to 2010 is a really, really bad idea. Now if I do it as just doing the centering without doing the scaling of the values in my linear column and then getting the resulting quadratic column, now the condition number of my calculation is basically 10 to the 4. So all I did was I just centered the numbers, I subtracted off a mean, and things are much, much better. So now I've got 10 to the 4, I'm going to lose about 4 digits of precision relative to the 16 that I would hope to have. So that's already a huge improvement and goes from taking a calculation that is numerically not going to give you a reasonable answer to one where you will get a reasonable answer. And now if I do it with here, I've gotten it even better. Now I've basically got a condition number of 10 to the 1. So I basically only lose 1 digit of precision in doing calculations with X transpose X when I do it this way. So again, sort of the take-home message that I see in this is oftentimes there's an easy solution, but if we proceed ahead naively, we can do something that's really, really naive, that's going to basically mean we can't do the calculation. Okay, any questions about that? Okay, so let me close by saying that what we're going to do next time is start thinking about matrix factorizations. And so the basic idea is oftentimes in statistics we want to do this calculation. Either we're doing a linear regression, so we have X transpose X inverse, X transpose Y, so that falls in this form. Or if we're doing optimizations, we often need to work with a system of equations like this. Or if we have an information matrix and we're trying to invert that information matrix to get an asymptotic covariance matrix in a statistical context, we need to do a calculation that involves an inverse. There are lots and lots of other examples. So this is sort of the canonical problem that we need to solve in doing a lot of statistical calculations. And what we're going to see is when we do this calculation, we're essentially almost never actually going to explicitly compute the inverse of that matrix. Rather, what we're going to do is we're going to take the matrix A, factorize that matrix into 2 or 3 other matrices, and then do the calculations with the factorized matrix. So when we come back on Friday, we'll start talking about those factorizations. Hold on 1 second.